Chapter 3: Internal Energy and Enthalpy. Section 3.3: The Joule Experiment. Joule designed this experiment to study how the internal energy of a real gas depends on its volume under constant temperature condition. So over here we have the experimental apparatus. There are two compartments separated by a valve. Right now we have a real gas on the left hand side, vacuum on the right hand side. We have thermometers to monitor the temperature and the temperature change. And this system is well insulated. Therefore we know Q is 0 and dQ is 0. There's no heat exchange between the system and the surroundings. And of course, because it's vacuum, there's no energy transfer between a system and vacuum. A vacuum cannot give energy. A vacuum cannot accept energy either. And now we open this valve. The gas will fill both compartments. The volume changes. And Joule looked at the thermometers. He found that there's no temperature change. And then he did some derivations. First, dQ is 0. There's no heat exchange because the entire system, both containers, are well insulated. And also, there's no work. This system did expand against vacuum, but if you look at the equation for expansion work is negative integral P external dV. This time P external is exactly 0. Expansion against vacuum means work is 0. Well, you cannot do work to a vacuum because a vacuum cannot either give energy or accept energy. Therefore dW is 0. Since dQ is 0, dW is 0, we have du is equal to 0. And also we can express du in terms of dt and dV, assuming u is a function of temperature and volume. Therefore du is delta u over delta t times dt plus delta u over delta v times dV. We also need to pay attention to the subscripts. Over here we hold volume constant, here we hold temperature constant. And again, Joule looked at the thermometers and found no temperature change. Therefore dt is 0. Also we have du is 0. Then 0 is equal to 0 plus this. Therefore this has to be 0. Now we know dV is non-zero because the volume changes. Therefore dV cannot be 0. The conclusion is delta U over delta V on a constant temperature condition has to be 0 based on this Joule experiment. However, the conclusion is wrong. Joule later used a more accurate thermometer and actually detected a very small temperature change when this real gas expanded against vacuum. So if we look at this equation again, this part later was found to be non-zero. du is still 0, but since this dt term is non-zero, then this part is also non-zero. He later concluded that the internal energy of a real gas did depend on its volume. The dependence is small, almost negligible, but it's there. And there's a reason. There's a theoretical basis for that. Because if we change the volume of a gas, for example in this situation, on average the distance between gas particles is longer here than here. When we have a larger volume, we have a longer average distance. And when the distance between gas particles becomes longer, both the attraction and repulsion between gas particles gets smaller. Therefore, the potential energy changes. The internal energy changes when the volume changes. Again, in this experiment, the system is well insulated, so we have dq equals 0. dW is 0 because the system expands against the vacuum. And that means the external pressure is 0. And the work is negative integral p external dV, therefore it's also 0. du is 0. And also u is a function of temperature and volume. So we can express du in terms of dt and dV, two terms. Over here, delta U over delta T on a constant volume condition is simply CV. It's just because when volume is constant, delta U is just delta Q. Delta Q over delta T, that's just heat capacity C. So we have C sub V here. And this term, we'll keep it. This is called the internal pressure. When the temperature change is very small, we can make approximations. So delta U is simply the integral of du, and then it becomes the integral of CV dt and the integral of delta U over delta V dV. So we have two terms. Again, when the temperature change is small, we can say, well, the first integral is CV times delta T. Delta T is T final minus T initial. And we're going to assume this delta U over delta V is roughly a constant as long as the volume doesn't change by much. So we copy it here and we have delta V here. Okay, this is an approximation for us to have a semi-quantitative understanding on how U depends on V. Now again, delta U is 0 because Q is 0, work is 0, so this plus this is 0. Now we can compute this delta U over delta V. It's simply negative CV delta T over delta V. So we get this expression. Somehow, if we measure the temperature change, the volume change, and if we know the molar heat capacity of the substance, we can compute this. We can compute delta U over delta V, and it's non-zero for a real gas. By the way, this is 0 for an ideal gas. So if we do the same experiments for an ideal gas, after expansion, there's no temperature change. But if we're doing this experiment on a real gas, the temperature will likely change. Again, in the Joule experiment, somehow we can determine delta U over delta V on a constant temperature condition. It's negative CV times delta T over delta V. For a real gas, delta T is very likely non-zero, so this is non-zero. For ideal gas, well, delta T is predicted to be 0, and then delta U over delta V is 0. It's just because for ideal gas, U only depends on temperature. We're holding temperature constant here, so this has to be 0. Now let's derive the exact expression for this delta U over delta V. We will use the triple product rule again in calculus. In the triple product rule, we need three variables, U, V, and T. So now we have UV, VT, TU, and then pay attention to the three subscripts. The product of these three terms is -1. And therefore, this delta U over delta V under constant temperature condition is -1 divided by these two terms. So right here. And now we're going to use the reciprocal rule. This delta T over delta U on a constant volume condition is the reciprocal of C sub V, isochloric heat capacity. So we put C sub V here, and then over here we can flip this as well, as long as we have the same subscript U here. So the reciprocal of this is delta T over delta V on a constant internal energy condition. For an ideal gas, delta U over delta V is 0, so this is 0. and therefore we have this is 0 for ideal gas. Well, what does this mean? If we somehow can hold the internal energy of an ideal gas constant, then its temperature is constant. It does make sense. If the internal energy is constant, then its kinetic energy must be constant, and therefore its temperature must be constant. Again, this is the Joule experiment. The exact derivation of delta U over delta V results in this expression. It's negative CV times delta T over delta V under constant internal energy condition. For all matters, we can prove this. Delta U over delta V under constant temperature condition is T times delta P over delta T under constant volume condition minus P. We will prove this in chapter 5. For a van der Waals gas, that means we can use van der Waals equation. We can evaluate delta P over delta T. It's NR over V minus MB. Alright, we can plug it in and we can simplify this expression. So this is T times delta P over delta T, and this is just P. So we get AN squared over V squared. That means for a van der Waals gas, its internal energy does depend on volume, and the dependence is positive. It's AN squared over V squared. Actually, it reveals a flaw of the van der Waals equation. It's just because if you think about the internal energy, there's got to be attraction and repulsion. So over here we see only the attraction term. Now let's still use this expression from the van der Waals equation. Alright, we just plug this in, AN squared over V squared here. So negative C sub V times delta T over delta V is equal to AN squared over V squared. When the internal energy is held constant, we have simply dt over dV is equal to negative AN squared over CV times V squared. So this equation comes from this equation. We just have both sides divided by C sub V. And over here, we can convert those partial derivatives to the just ordinary derivative over here, because we have this condition here. Just assume we have a system with constant internal energy, and then we have this. Therefore, dt is negative AN squared over CV V squared dV. Looking at this, we can integrate both sides. After we integrate both sides, delta T is just AN squared over CV, and then times the integral of negative 1 over V squared dV. The integral of 1 over V squared dV is just 1 over V, and therefore we have this expression in the end. For a van der Waals gas, the temperature change depends on the volume change. It's AN squared over CV times the reciprocal of final volume minus the reciprocal of initial volume. What does this mean? Well, a couple things. This term depends on A. So if you have a larger attraction, you'll have larger delta T. Smaller A, smaller delta T. For ideal gas, A is 0 and delta T is 0. That's number 1. Number 2, let's look at expansion. When we have expansion, well, V final is greater than V initial. Therefore, this is actually negative. Delta T is negative. The temperature has to decrease when the volume expands. And by looking at this parameter A, we realize that when the volume increases, the distance between gas particles increases. That means we'll have like smaller attraction. How can we take this change in attraction into account? Somehow we'll have to overcome the attraction with some kind of help. In this case, the system is well insulated. We do not get any external help. So to overcome the attraction, well, we have to convert part of the kinetic energy to potential energy. And if we have to convert part of the kinetic energy to potential energy, the kinetic energy of the real gas decreases, and temperature is the measure of the average kinetic energy, and then temperature decreases. We have a negative delta T. Again, if we use van der Waals equation, If V final is greater than V initial, that means we need to overcome attraction. Where does that energy come from? From the decrease of kinetic energy, and therefore the temperature decreases. Let's look at 3 numerical examples. Well, the first one is actually an analytical example. So we'll just prove this for a van der Waals gas in this Joule experiment. We will just assume the molar isochloric molar heat capacity is constant. U, the internal energy of a real gas, actually depends on pressure, volume, and temperature. But out of these 3 variables, only 2 are independent variables. We will choose volume and temperature for convenience. And then U is a function of temperature and volume. du is delta U over delta T times dt plus delta U over delta V times dV. And then let's evaluate this part. This part is simply delta Q plus delta W over delta T. And because volume is constant over here, it's just C sub V. We can also prove this later in chapter 5. So we have du is equal to CV dt plus something times dV. That something is T times delta P over delta T minus P. For a van der Waals gas, we have this derivation. This part is just AN squared over V squared. Now we have a simple equation for du. It's CV dt plus AN squared over V squared dV. Only 2 terms. This term depends on the temperature change. The second term depends on the volume change. For a van der Waals gas with a constant U, then du is 0, CV dt is negative AN squared over V squared dV. And we can then integrate both sides. We have the expression for delta T. Delta T is simply this. Or we can just divide the top by n squared. We can divide this by n. We can divide this by n. We can divide this by n. And then we have all those intensive properties. Delta T is A over CVM times, well, the difference between the reciprocals of the final molar volume and the initial molar volume. And by the way, all these are intensive properties, and delta T is an intensive property. Now a numerical example. Example problem 3.3.2. We'll look at a nitrogen gas. Let's estimate the temperature change of 1 mole nitrogen gas when it expands against vacuum from 2 liters to 25 liters. We have the values of the van der Waals parameters A and B over here. Unfortunately, they are not really in the SI unit. Decimeter cube, this is actually liter, and this is a liter squared. And then we have bar. Bar is not an SI unit either. So, but still, we're going to do the calculations. First, we convert this A from non-SI units to SI units over here. Well, again, this is decimeter to the power of 6. We convert it to 10 to the power of negative 6 meter times meter to the power of 6. And 1 bar is 10 to the power of 5. So therefore, we did this conversion. Alright, this 1.3 becomes 0.13. Alright, and then we have the molar volume for the gas in cubic meter per mole. It's just because meter is an SI unit. Now we compute delta T using this equation. We're plugging all those values in the SI units. In the end, we get negative 3 Kelvin. So when this nitrogen gas expands, the molecular distance increases. And we'll have to somehow overcome the attraction, and we need energy to overcome the attraction. Where does this energy come from? Well, we have to borrow from the kinetic energy of the nitrogen. That's why the kinetic energy of the nitrogen decreases, and therefore the temperature of the gas decreases. Again, this is a good example for the transformation of energy. In this example, kinetic energy is transformed into potential energy. And if we look at this equation again, we see only the parameter A. We didn't even see parameter B. For the van der Waals equation, it's a flaw of the van der Waals equation. Alright, because when we increase the volume, the distance between gas particles increases. Both attraction and repulsion should be affected. Both attraction and repulsion should decrease, and both should play a role in the temperature change of the real gas. Now another numerical example. This time we just replace nitrogen with HCl. That's the only change. We still have the gas expands against vacuum from 2 liters to 25 liters. We will still use the same equation, but this time we have a larger A. Just by looking at this, if we have a larger A, we'll have a larger delta T. And it's true. When we do the calculation, we see the temperature decrease is now negative 8 Kelvin for HCl. When HCl gas expands, again, the distance between gas particles increases on average. Therefore, the attraction decreases. Somehow we need to overcome the attraction to increase the volume. And where does this energy come from? We need to convert some of the kinetic energy into potential energy, and that will decrease the temperature of HCl. And also, by looking at this equation, delta T is proportional to A. For HCl, we have a larger attraction than the attraction between nitrogen gases, and therefore we have a larger A. When we have a larger A, we have larger delta T. We can see more obvious temperature change, in this case with HCl as our system. Now let's back to the ideal gases. For ideal gases, A is 0, B is 0. There's no attraction, there's no repulsion. So supposedly this delta T is just 0. Alright, so the expansion of an ideal gas, okay, against vacuum will make no change in its temperature.